Here we are, good morning. It's the physics video lecture, Physics 105B, video lecture 26. So, what are we talking about today? Integration with the purpose of getting moments of inertia. And I'll put a little background up here, and we'll kind of review what we did last time and take it another step further. So, we have the moment of inertia, and that's mass times length squared, r squared delta ij, and it's xi xj. We know that the moment of inertia, and it's integrated over the body. We know that that inertial tensor is going to be diagonal in a case of a symmetric body, and we want to spend some time doing these integrations now, culminating in the ellipsoid, the moment of inertia of the ellipsoid, and we'll use some new integration technique that we've been discussing. So in order to get this, and I'll say one more thing, since it's diagonal and there are certain properties of these with the symmetry, you can often get by with doing a single integral and then switch letters and stuff and get the entire one. So that's good. Okay, so the next thing was that we wanted to do the integration for many variables, so integration in r to the n. And what we had was the transformation formula. And that's what we're going to do some more with. And I'll set everything up, and whatever I leave undone would be on the homework. So how did this go here? We had let phi of C be a coordinate transformation. And I gave examples last time, and I'm going to give examples again. Plane polar, spherical polar, cylindrical would all be transformations. And d phi of C be a matrix d phi sub I d C sub j. That's called the Jacobian matrix. And then we have its determinant. And we've got the determinant of this d phi magnitude, which will be the determinant of this matrix and its magnitude. And once again, the example, we had x equals r cos phi, y equals r sine phi. In this nomenclature, we would have been saying phi sub 1 is equal to c sub 1 cos c sub 2. So yeah, we're usually not going to go here. C sub 1 sine c sub 2. That's how we're assigning these variables. Okay. And the Jacobian we already wrote out for this thing, and then the determinant was just r. Okay. So that's how we're thinking about these. We're going to be going between different letters and variables, so we just have to deal with that. So the transformation formula looks like this. So if we're integrating over some region in n space, that's what u is here, it's a region. We have a function of phi of c. I'll leave off the vector signs, and then we have that, I'll write the whole thing out, the determinant magnitude determinant of this dv, and then dnc, so n variable, that is equal to, I'll just write f of y dny. I guess I'm inconsistent. I'm writing the vector nature of it there. Okay, y has the n variables. You know, those were the phi sub 1 to phi sub n, so to speak, when you transformed and renamed them. Okay? And the region here, this is very important, is the mapping of this region onto here. Now I said this is just like regular U substitution from the fundamental theorem of calculus. So let's do an example right underneath this thing. Example for n equals 1, different variables, but well, we can do this. So suppose we have from A, I'm gonna leave room, put one row under here as well. So suppose we have integral from A to B of 1 plus x squared 2x dx. Okay. You can see what I'm driving at here. And if we were to do our U substitution, we would say, or I'll use a Y substitution to use here. So y is equal to 1 plus x squared, dy is equal to 2x dx. Okay. So if we're to do that, then what would our integral be? It would be y dy, okay, 1 plus x squared 2x dx, y dy, and the limits of integration would be from 1 plus a squared, because of the 1 plus x squared, right, 1 plus a squared, to 1 plus b squared. Okay. And you could go ahead and do that. That's a very basic, but you can see what I'm driving at here. The dy, the 2x dx, corresponds to the determinant d phi dn, or dc, yeah, d phi dn c. Okay. So that's the correspondence there. And in one dimension, this is literally what we're doing, and in n dimensions, it's also what we're doing. There's a way to discuss determinants and show that they are essentially associated with volumes. Anyway, I have an interesting proof maybe later, but for now, we're just going to accept this as the n-dimensional generalization. The proof is worth it too. It's a proof idea. If you're able to diagonalize this matrix and then in its diagonal form, right, diagonalize this matrix, then in its diagonal form, its determinant is just the product of all the diagonals. And so the new versus the old volume element is actually pretty clear. Okay, let me rewrite this one more time. So I'll write or integral, and I'll just do the interval AB. So that's a region of space, right? AB, and I've got my 1 plus x squared 2x dx. And then over here, I have my new region is from 1 plus a squared to 1 plus b squared. It was AB, now it's 1 plus a squared, 1 plus b squared, y dy. So now my limits of integration, instead of from a to b, I'm expressing them as a certain region of space, which would have been, just for the sake of argument, here's the origin. I've got a to b here, and then say that maps onto, I'll just say it maps onto 1 plus a squared, 1 plus b squared, just for the sake of argument. Okay, so there's a interval here, and it maps onto this one. Okay, so that's what these things mean here. And we already did one application of this to find the volume of the ellipsoid. Did we find the volume of the ellipsoid or the area of the ellipse, I believe. Okay. So the one application was to find the area of the ellipse. So I'm going to so we have from last time, I'll just write ellipse x squared over a squared plus y squared over b squared less or equal to 1. And for that, we found the area was equal to pi AB. And for the ellipsoid, did I do that last time or not? See how much we're going to review here. Ellipsoid we're going to save for later. So we're working on the ellipse. And our next task is to use this formalism to get the moment of inertia of the ellipse. Okay, so we have ellipse here, so that's its area. Disk. And the moment of inertia of the disk, I'll write this out in words. We're going to use this moment of inertia. For the disk, and that was I equals 1/2 m radius squared. Uniform disk of radius r. Moment of inertia, we're talking about the one that's right, we're rotating about the axis coming out the board. That's the one we're going to work with. Okay, so this time we want the moment of inertia of that elliptical lamina, that flat elliptical uniform object. And the moment of inertia, I'm going to mirror what we have up here. So on the right side, leave yourself a lot of room to the left. Moment of inertia, what we're looking at is dm x squared plus y squared for the ellipse. Ellipse, A comma B, right? It's the ellipse as defined up there. And over here, I could say, since the dm is going to be density d area, it's going to be m over pi AB, and then I'll have double integral dx dy x squared plus y squared. And again, I'm just going to write ellipse. Okay. So how's that going to transform using the transformation formula? Well, as we did last time, we're going to have we're going to stretch x and y by the length a and b. Okay. So the left side formula up here, we'll still have the m over pi ab, but we're going to transform this part. So we have m over pi ab. Let's see, am I working left? Yeah, I'll just write this down. So we will have, for the left integral, m over pi ab. We're integrating over the unit circle. So I can do two integrals here. I'll just write unit circle. And the transformation that we had last time is the same one we'll use this time. So we have, kind of reversing the order here, we have d, c, d eta. So that was our dm comprising this and this. The determinant of dc was just ab, magnitude of the determinant, and then the function that we're looking at is the x squared plus y squared. X squared plus y squared. So that's a squared c squared plus b squared eta squared. Okay, so we're doing the same thing we did last time, except we don't just have one here, okay? Because we now have that function there. Last time it was just dx dy. So that's the transformation, where x, a times c, y, b times eta. And the Jacobian we did last time, determinant is just the two diagonals, which are a times b, and then there's that function there. Okay, so now we're doing this on the unit circle, so I'm going to take this integral, right? It can be turned into two integrals, right? But if I do the first one and understand what I'm doing, I'll get the second one for free, okay? Just by relabeling. So we're integrating this over the unit circle. That's what this next integration is. And then when we're done, we'll multiply it by m over pi ab, and we'll be done. So doing this over in fact, I'll keep the m over pi ab here. M over pi ab. And we're integrating over the unit circle. Before I do that, I have a cubed b. A cubed b. And now I have double integral unit circle dc d eta c squared. So now we're just going to rename things. Okay, since this is a unit circle integral and this is what we would normally call x, okay, we have, and I'll just keep these along with us. We have m over pi ab a cubed b, and now this double integral, since it's over the unit circle, it's dr d phi. The d phi is 0 to pi, the dr is 0 to 1. Okay, this is the crucial step. And the c squared, again, is essentially, not just essentially, it's from the x direction in the unit circle, so it is r squared cosine squared phi. Okay, so that's the translation from this integral here to this integral here. And now we're ready to just finish this. M, we've got pi ab, we've got a cubed b, and now how about this? Oh, one mistake here. In fact, I have enough room. Dr d phi r. Remember, that's the transformation. That's the transformation to plane polar coordinates. Dr d phi r, or r dr d phi, right? And then we have the r cos phi squared. Okay, so let's call there, makes all the difference. Now the integration is going to be r cubed from 0 to 1, so it's going to be r to the 4th over 4 from 0 to 1, so that just gives us 1/4. Okay. And the integration 0 to 2 pi is going to be cosine squared of phi from 0 to 2 pi. So we know that that's 1/2 times 2 pi, so that's just pi. Okay. And now we can cancel those. We've got a squared, b goes away. So we'll have a very interesting result, equals m over 4 a squared. Okay, so yeah, make sure you see that this was the transformation of this integral to plane polar coordinates on the unit circle. That's why I have 0 to 1 for dr. And then the volume element was r dr d phi, so we got that. So that's transformation to plane polar coordinates. And now we have m over 4a squared. The second integral is going to work exactly the same, and we're going to get the b squared out of it. So we don't have to do it again. It's just renaming things. And the integral would be over a sine squared instead of a cosine squared, but from 0 to 2 pi, the sine squared is also going to have the same answer. Good, so m over 4a squared, and I have room here at the bottom, and I sub ellipse is equal to m over 4a squared plus b squared. That's a fine result indeed, because we see that when a equals b equals r, we end up with mr squared over 2. Okay, so there we go. So what we want to do next is set this process up for the sphere to the ellipsoid, and see how much of that we did, see how we're doing time-wise. We got nothing but time. All right, fantastic. Okay, in fact, I'm going to I'll leave this up here, the formula, and erase this right here. So yeah, very important result, and you saw how we did that transformation formula. So this side was our ellipse, and then here we were integrating over the unit sphere, and the transformation took the unit sphere onto the ellipse. Okay. So we're going to do the same thing now for the ellipsoid. So moment of inertia of the ellipsoid. And for this we have to, since we're going to be mapping the sphere onto the ellipsoid, we have to have a couple of things set up for us. So we're going to say x squared over a squared, y squared over b squared, z squared over c squared, less than equal to 1. Those are all the points x, y, z that belong to the sphere, to the ellipsoid. And the mapping of the sphere onto the ellipsoid is just via x equals a c, y equals b eta, z equals c zeta. Right, so my c 1 through n is actually 1 through 3, and I'm renaming them c eta zeta. And the determinant of d phi, which I'm going to call it here with respect to these things, just as before it was AD, it's just ABC, because we're just extending or contracting the coordinates in either of those 3 dimensions. Right? So the Jacobian matrix is just a diagonal matrix, ABC, and its determinant is the product, ABC. So the other thing we need is, for our sphere, I is equal to 2/5 m r squared. Did I assign that last time? I think I did. That's definitely something we can get out, and we can get with, there's a couple different ways to get this result. So if you know more than one way to get it, go ahead and get it. We had talked about it just in terms of the spherical polar coordinates. Good. You know, based on what just happened, on that result that I just erased, we could pretty much guess what the inertial tensor is going to be. We generalize what we just saw. But suppose we actually have to do the work. Then we're going to use this again. So this time, let's set this up. We have integral, I'll work underneath this time. We're going to have integral dm, and let's say we're doing x squared plus y squared. So since we're talking about the sphere, this is I sub 3, 3. That's about the x3 axis, or the z axis, if you want. Okay. And this is a good one to work with in this case. So x squared plus y squared. And it will be m over 4/3 pi ABC, because that's the volume of the ellipsoid. Yeah, did we do the volume of the ellipsoid? Actually, I don't have it written down. Doesn't matter. Let's label this. We haven't done it yet, we should have, and you can do that the same way we did the area. In other words, these transformations where the function is just 1, the transformation from the 4/3 pi times 1, which would be the volume of the unit sphere, and then 4/3 pi ABC is the volume of the ellipsoid. So that is our density from our dm here. And then we've got the integral, I'll even write a triple integral over the ellipsoid dx dy dz times x squared plus y squared. Okay. So that's what we're looking for. How does that work with the transformation formula? Well, the m over 4/3 pi ABC gets pulled out regardless, so that 4/3 pi ABC, then we're going to have an integral, again, the determinant d phi dnc turns into the determinant, I'll write it here first, it's the ABC dc d eta d zeta, okay. And it's a triple integral as well. And then we have here the, so this was x squared plus y squared, we have a squared c squared plus b squared eta squared, as before. So that's our transformation formula. This is the answer that we want, but this is the formula we're using to get it. So let's do another step. Because you can see we're going to pull out a lot. We're going to have m over 4/3 pi ABC. We pulled out ABC, that actually cancels that right away. Now we're doing these integrals, and we're just going to do the first one again, because we can get the other ones by renaming. Okay. And the first one is integral triple integral. We've gotten the ABC out. We also have an a squared. Now, let me rewrite this. So, ABC will pull out the a squared. And now we're just doing one of these. dc, d eta, d zeta. That's just Greek xyz. Okay. C d eta, d zeta. C squared. So really the same thing we did a moment ago, except this is unit sphere instead of unit circle. Okay, we'll go ahead and use this side of the board. Okay. Okay, I'm just carrying these along. 4/3 pi ABC, a squared. Just because they all came from a different place, we can simplify anytime. Now, what is this over the unit sphere? Now, the unit sphere, and this refers to the x component of the unit sphere, just names. So for the unit sphere, we have integrals r squared sine theta dr d theta d phi. So the r is the unit sphere at 0 to 1, the theta is 0 to pi, and the phi is 0 to 2 pi. Okay, so there's the translation that I'm doing for this unit sphere. And now I have my function. That would be the x squared. So that would be r sine theta cos phi squared. So now there's the integral. And you see we have to do one for each. So for the r, we have r squared, r to the 4th. So that's r to the 5th over 5 from 0 to 1. So that just gives us a 1/5. Okay. And then we'll do the phi next. We've got the cosine of phi, d phi from 0 to 2 pi. So that's minus sine from 0 to 2 pi. Oh no, that was almost, I would have been wrong. We've got cosine squared of phi, okay, from 0 to 2 pi. So cosine squared would be 1/2 from 0 to 2 pi. So that is just going to give us pi. And then we have an integral. This one we'll have to think about a little more. We have a sine cubed. Okay, that's cosine squared. We have a sine cubed. Sine cubed theta d theta from 0 to pi. And this one, we can do integral 0 to pi 1 minus cosine squared theta sine theta d theta. And then the sine theta d theta integral is minus cosine theta. So we just get 2. And then minus cosine squared sine theta, that's minus the integral of cosine squared sine theta, so minus cosine cubed theta over 3, except since plus. So we've got the 2, and we have this 0 to pi 2 minus 2/3 equals 6/3 minus 2/3 equals 4/3. Okay, so we have it all. Well, wasn't going to do this. Okay, hold on. I guess we have it all here. Let's write it down. Don't know what I'm going to leave for you guys. Okay, so here's our result. If all went well. And then we'll regroup. So we have, now we can actually do this. We have 3m over 4 pi, ABC cancels. We've got a squared here, and all of this gave us 1/5 pi over 5 times 4/3. And we have 4, 3, pi cancels. We have m over 5 a squared. Good. M over 5a squared. Now the full result would have done the same thing with the b squared, same argument as before, by the way. So we've gotten m over 5b squared from this one. And so we have, for our result, I sub 1 equals m over 5 a squared plus b squared. We just got this one. And you'll notice if a equals b equals r, we'll get a 2 in the numerator, r squared, so we'll end up with that 2/5 again. So this one we could have guessed as well. Just like I said, we could have guessed it. We could have guessed it. Okay. So I was going to leave some of those steps to you guys, but here they are. Let's summarize what we have. This is better. Okay. For the ellipsoid, ij, once again, let's go ahead and write this out. R squared delta ij minus xj. So we've got our ellipsoid, x squared over a squared plus y squared over b squared plus c squared over c squared less or equal to 1. And then the moment of inertia now, or the inertial tensor, since we have that now, is m over 5 b squared plus c squared 0, 0, 0, m over 5 a squared plus c squared. And the one we just found was the third, 0, m over 5 a squared plus b squared. Okay, so they're all different. They can be. Good. So yeah, we only had to do one integral, so to speak, in each of these cases, but we did have to get the volume of the ellipsoid and stuff like that. So homework for this subject really, if I missed a piece, did I do the volume of the ellipsoid last time? So calculate the volume of the ellipsoid. So if you do these, you'll, or just repeat these, make sure you see what happened. Okay. If you do it a couple times, it's pretty transparent. I don't have time for that proof today, but maybe we'll even do the proof before we leave the subject. This is a good place to halt this. Okay, good. See you next time. A little more integration, and then back to the dynamics.